Again, just to review, these are our options here. Either the ground rises to eye level, or you bring your eye level to the ground, and we will, in the end, find a angle at which they utilized to derive the radius of a sphere using the angular resolution limit of the eye, and we will derive a radius for this sphere at 3,959 miles to 3,978 miles. At the end of the series, you can decide which version better represents the reality of essentially what a horizon is. Is it a physical phenomenon, or is it an optical one? The assumptions that we're going to make are: 1, the perspective changes with the observer, especially with regard to observer height and their distance to a tangible object like a floor, a wall, or a ceiling. That objects get smaller with distance, that small objects disappear from vision, and that the horizon rises to eye level. Our objectives we've gone through before. This is now part 3 of the 6-part series, so we have at this point discussed the 1-point perspective, explained the basic optics of a lens system, demonstrated the horizon at eye level, and we have gone through perspective changes with the observer, especially with regard to height changes and their effects on orthogonal and transversal lines. So this is part 3. Now we're going to get into the angular resolution limit itself, Airy patterns, Airy disks, Rayleighs criteria, the diffraction limit, differential angular compression and the resolution of images above and below the vanishing line, angular size stability of the sun and moon, the cause of a sunset, the importance of Polaris with regard to distant vision and position, and the effects of magnification on perspective and its effects on diffraction. So this we'll get into angular resolution here first. The formula for angular resolution with regard to Rayleighs criteria is given by the following formula, which is theta in radians is equal to 1.22 times the wavelength of light going through the spherical aperture or circular aperture divided by d, the diameter of that aperture. And so this angle is proportional to the wavelength of light divided by the diameter of the aperture multiplied by a constant of 1.22. And this constant is derived from a mathematical construct called a first-order Bessel function, which is used in a variety of areas, not just angular resolution. It's conceptualized similar to ripples from water spreading out in a circular diffraction pattern. It has wave minimums and maximums that decrease in amplitude, spread out into the distance, and eventually drop to 0. It's essentially like a sine function, but with progressively decreasing amplitude, like a damping effect. And so the 1.22 is essentially a constant that allows us to look at the central maximum, which is what we're interested in, as we'll see. So in this case, instead of water, the diffraction pattern is made by light scattering through an aperture or pinhole, and the circular ripple pattern is called an Airy pattern. And just like with water, wave amplitude minimums and maximums are created, each with an increasing diameter as they move outward. The central maximum, which is the bright circle fringe in the middle, is called the Airy disk, and the dark circles are the minimums. So here on the left we have a circular diffraction pattern of water, and on the right you have the circular diffraction pattern of light. And that creates this Airy pattern, and the bright fringe in the middle is the Airy disk. And the 1.22 describes the relationship to that central disk. So the radius of an Airy disk can be derived from the radius equal to the length of light from the aperture source to the to where the image is projected times the sine of theta. If the aperture diminishes, there's more diffraction and the Airy disk enlarges. And if the aperture gets bigger, there is less diffraction and the Airy disk gets smaller. So essentially the angles get wider if you shrink this circular aperture down and you're trying to squeeze light through this aperture. It essentially sprays out at a larger angle. versus if you make the aperture larger, the angle at which the light is bent around that aperture is less, and it hits the image in the background essentially more straight on, and the angle is less. So from Young's double slit experiments and Huygens principle, we know that light traveling through an aperture diffracts as if it were many apertures, and it essentially interferes with itself, yielding the same diffraction pattern as multiple slits. I won't get into the specifics here, but by dropping normal lines from converging rays, traveling different distances to construct the diffraction pattern, a formula for the diffracting angle theta can be derived such that theta in radians is equal to 1.22 times the wavelength divided by the diameter of the aperture. This angle theta, which represents the radius of an Airy disk, would also represent the distance at which two distinct Airy disks would overlap by 50%. So again, if we just put two different light sources and shot them through circular apertures, we can approximate these two until a certain point. So when the two non-uniform light sources are used and we have two distinct Airy patterns, we can resolve the two disks until they are overlapping by 50%. And this is called Rayleighs Criteria. And once the Airy disks overlap by more than a half or more than 50%, the image cannot be resolved as distinct. The two objects become one, and one is missing. If the disks are larger with smaller apertures, and we're recall that the angle gets wider if we shrink down the aperture. So if the disk gets larger as we make the aperture smaller, they overlap more quickly and are lost more quickly than the smaller disks with larger apertures. Therefore, the smaller the angle, the better the resolution. Within our variables, larger wavelengths and smaller apertures diffract more and are less resolved, versus larger apertures and smaller wavelengths that diffract less and are more resolved. So here we have some of these Airy patterns with their Airy disks becoming progressively overlapped. So at 0% overlap, it's still resolved. We're going to overlap the disks a little bit more. They're somewhat resolved still, but then at 50% overlap, you see it as one pattern, and it is unresolved. So this distance is the same as the radius of the Airy disk. Recall that the radius of the Airy disk is essentially the point at 50% overlap between two disks. So as the patterns overlap, you'll notice intersections between the bright and dark fringes. These are overlapping constructive and destructive interference zones. So as the two patterns get closer, the interference points will start to lessen in number, and at 50% overlap of the disks, you will see that the pattern looks essentially the same. So you can draw constructive lines going through these overlap points, these constructive interference points, and the destructive interference points. And what you'll see is that these overlap points get fewer and fewer, and eventually we are resolving one pattern. And we'll show that here momentarily. So here we have two disks. The two central Airy disks are far apart here, denoted by the brown line. And note that we have all these numerous crossover points. So in the dotted lines, and then I've just outlined essentially three constructing zones in their radius or their distance from one another with the green line. And so you can see the corollary to the two diffraction patterns I overlapped in the upper left, and I've outlined their number in the blue lines. So as we go through this, you'll see that they get fewer and fewer, and the angle between the constructive zones gets wider and wider as the two Airy disks get closer and closer. So here we've moved them a little bit closer, closer again, closer again, closer again. And here we are at just prior to 50% overlap. And already it's very difficult to distinguish the overall pattern. Take a look at the upper left. Again, you still resolve the two circles in the middle, but just barely. And so this is starting to look very much like one pattern. You can see the three constructive interference zones that I've outlined, and the distance between them with the green line. And again, our brown line is the distance between the two patterns. So now let's overlap them a little bit more, and you get this. So now we're at 50% overlap between the two central disks, and the observer perceives one pattern. Also, we now only have one interference zone extending vertically. So if you look in the upper left, you cannot resolve the central disks as two essentially anymore. We have one constructive interference pattern vertically, and the object has become one is missing. So if we return to our lens diagram, you can see how two rays merge with distance and height above and below our eye line. As the object gets further or reduces in height nearby, the two rays extending through F1' and F1 get closer, and the information starts to overlap. So I've just kind of taken the Airy disks out, the Airy patterns out, and they are modeled here with the brown line, allowing the two rays of light to get closer and closer to one another, and you start to see constructive interference patterns, but at a certain point the image is unresolved and it becomes a single ray of light. So these two rays of light that are creating the context for an image, we know from Airy Criterion that we need these two rays to intersect behind the retina to create an image on the retina. At a certain point, they become an indistinguishable single ray of light. So at 50% overlap, any aspect of an image will be lost if it is within this angle. So this angle is theta. And images converge behind your eye, again, with at least two rays above the eye line and two rays below. So again, the top of the tree is the two rays above your eye line, the bottom of the tree is with the two rays below in this example. So if the two convergent rays below the eye line overlap by 50%, the two rays become one, no image convergence occurs, and the bottom of the object disappears. So in this case here, you can see how the two rays coming off the bottom of the tree are closer than the two rays coming off the top of the tree, because the bottom of the tree is shorter than the top of the tree in this case. So as we extend this tree outward to the left, let's say, the two rays for the bottom of the tree are going to get closer and closer and closer, and the two orange rays will as well, but at a less of a rate. And the two rays below, the blue rays will approach that angular resolution limit. They will become unresolved. Those two blue lines will essentially become a indistinct single source of information, and it will not be resolved as an image. So some notes here before moving on. The two light sources send out any number of wavelengths along the visible spectrum. Once they hit an aperture, they separate. And so we are examining two coherent sources interfering with one another, reds with reds, blues with blues, etc. So below is the diffraction pattern of white light with a red laser diffraction overlay. You can see that the red is lining up with the reds of the diffracted white light. So as the white light separates, you can overlay with any other laser, and those wavelengths are going to go to that location. And what's also noticeable here is that the red is creating essentially a larger radius disk than the blues are. The blues are more centrally located, and what that means is that the reds are actually more diffracted than the blues, and can become less resolved sooner. Also of note, Abbe similarly derived the resolution limit, as did Rayleigh, and his formula takes into consideration the numerical aperture of the observer such that illumination becomes a variable of significance. The brighter the field and the greater the illumination, the more resolved the object. For spatial angular resolution of the eye and camera systems, however, we will use Rayleighs criteria, but I want you to keep in mind that illumination does affect resolution. So as things are dimmer, they are less resolved. So as you look through longer and longer amounts of atmosphere, let's say, and things are getting, or the light is that's coming to your observer, either your eye or your camera system is becoming less and less, things can get less and less resolved. So with a cursory understanding of Airy patterns, using our formula and some variables, we can calculate the smallest resolution angle theta for the human eye. We can then take that angle theta and apply it to any distance d to calculate what the smallest diameter or height h that we can resolve. So let's do a practical example indoors before moving outside to large distances. So we'll see if we can see a small bug that is 20 feet away. So our formula for this resolution angle is 1.22 times the wavelength of light divided by the diameter of the aperture equals theta in radians. We're again, once we derive that angle, we're then going to use it within a right triangle, assuming that this is a essentially 90-90 degree small angle right triangle, although in reality this would be more like possibly more akin to a isosceles triangle, but because it's such a large distance away, we can use it as a right triangle. But we're going to use that angle to place our object within it as a certain height and a certain distance away, and we will see what that height is with that angle that we can resolve is. So we'll do an example here to kind of show what I'm talking about. So we'll say our bug is 2 millimeters and our wavelength is 500 nanometers. Our pupil diameter is 4 millimeters, and our bug is again 20 feet away or 6.1 meters. So plugging in for our formula, 1.22 wavelength divided by diameter. So we have 1.22 times 500 nanometers divided by 4 millimeter pupil, and we get a number in radians. We then convert radians into degrees. Recall that you just essentially multiply it by radians by 57.3, and you will get your angle in degrees. And so we have our angle, and now let's apply it to our right triangle for a large distance and small angle. And what you will see is that you can rearrange this formula then, right? So tangent theta is equal to height divided by the distance, and so height would be equal to d tan theta. And so plugging in d tan theta, we would get 6.1 meters. That's how far the bug is away. Tangent 0.00874, which is our angle, and we get 0.9 millimeters. So what you find is that if our bug is 2 millimeters, we can see it still, but if the bug is less than 0.9 millimeters, we can't. So the average resolution limit for the human eye is 0.02 to 0.03 degrees, or 1 arc minute. So 0.00874 is definitely a good kind of a best case scenario. So when there are no aberrations in a lens or other distortions altering our system, brightness or let's say dimness, refraction issues, and so forth, we are only limited by diffraction or diffraction limited. But since aberrations abound, for our purposes here, we will assume the standard 1 arc minute, which seems to be fairly common among multiple observation systems, including cameras. So let's go out to a large distance. The diameter of the pupil ranges from 2 to 4 millimeters in bright light and 4 to 8 millimeters in dark. The wavelength of light ranges from 400 nanometers in the purple range to 700 nanometers in the red. Our orange and red wavelengths are less resolved than the blue, but they are less subject to refraction and atmospheric scatter. So when we are looking at long distance photography, let's say, you might see more and more in the red range with longer distance, but it's going to be less and less resolved. Keep in mind that the red wavelength had a larger Airy diameter than the blues did when we diffracted out our white light example. And so those reds are less resolved, but the lower wavelengths also travel longer within larger amounts of atmosphere to reach our eye. The blues and the higher wavelengths get scattered out and they don't reach us, but we still see within the higher wavelength light range. So as you look at objects with distance, sometimes you'll be seeing them in lower wavelengths nearby with brighter light, and as the illumination gets dimmer and the wavelengths of light that you're seeing are in the higher range with distance, you might start to see more and more angular resolution coming into play. So with theta at 1 arc minute, we can now see how this resolution angle across a distance d limits the height and diameter of an observable object. So we can do this over any number of distances and solve for the smallest height as d tan theta. So on average, we lose 4 feet at 2 miles, 6 feet at 3 miles, 8 feet at 4 miles, 10 feet at 5 miles, and so on. Holding theta constant, we can also reverse the triangle to find out what the outdoor horizon distance is for a given observer height. So recall our horizon calculation as h1 over h2 equals d2 over d1, and essentially this is just representing that formula using the same resolution angle between the two heights and distances. So if the observer is at height 1 and then he moves higher to height 2, his distance at distance 1 is going to get larger at distance 2. So we can again rearrange our formula. If we're looking for a height across a distance, we can say height equal to d tan theta. If we're looking for a distance across a certain height, we can use distance equal to height divided by tangent theta. And we can do this over any number of heights and solve for the horizon distance equal to height divided by tan theta. So plugging in for both of these formulas, we already discussed the what we lose. So again, recall that we lost about 4 feet at 2 miles, 6 feet at 3, and so on. And then reversing this triangle for distance, we see 2 miles at a 4-foot observer height. We see 3 miles at a 6-foot observer height. We see 4 miles at an 8-foot observer height, and 5 miles at 10 feet, and so on. So another way to view this is that if my eye line is at a 4-foot elevation, I will lose 4 feet of information at 2 miles when theta is met against any tangible surface. So if my eye height is the same as the top of the object traveling away from me, it remains below my eye line the entire way and never crosses over the horizon. So again, recall in part 2 that things do not cross over different orthogonal lines traveling straight away from you. So it disappears as a single unit, like a point. So if an object is below my eye line and just stays below my eye line as it moves away from me, it does not disappear bottom first or top first or side first or any of that if there are no tangible obstructions against it. It will simply disappear as a single point. And again, that happens once it reaches the distance d that is equal to the height of the object being observed, or h divided by tangent theta. So again, if I'm at 4 feet, I'm going to lose 4 feet worth of information at 2 miles. If I'm at 6 feet, I'm going to lose 6 feet of information at 3 miles, and so on. So let's go into this a little bit more. So if I am 6 feet tall, I will lose my observer height worth of information below my eye line, which is 6 feet, at h divided by tan theta, or 3 miles. It will disappear as a whole, not bottom first, because it's entirely below my eye line. If I'm outdoors and the object were 12 feet tall and traveled away from me, I would lose the bottom 6 feet at 3 miles, which is my closer lower horizon, and the remaining 6 feet at 6 miles, where a 12-foot object would disappear as a point if it weren't for the ground making the lower 6 feet disappear first. So just to reiterate this again, so if I am watching a 6-foot, let's say I'm watching another 6-foot person walk away, and I'm at a 6-foot observer height, I'm essentially looking at the back of their head. When they reach 3 miles, I will lose that person, right? What if I was watching a 12-foot boat or something like that travel away? Well, at the bottom 6 feet is lost at that 3 miles, right? It's reached theta within my lower visual field, but there's still 6 feet remaining of that boat above within less compressed visual field lines. So that 6 feet now is going to take an additional 3 miles to disappear. So essentially my 12-foot object still disappears at 6 miles, but it does so differentially with the bottom first. So if I now direct my gaze away from the ground and away from those compressed lower visual field angles, and look to the sky, and now I view my 12-foot object, it's going to ascend into the sky away from me, it would disappear as a whole, as a single unit, not bottom first or top first or anything. It's going to disappear as a single point at around 6 miles, which is 12 foot divided by tangent theta, because no limitations were placed on the light rays reaching our position, like a wall or ceiling or floor. So if I were indoors and equidistant from a 12-foot ceiling and floor, let's say I'm in a giant hallway, and it's a 12-foot hallway, and I'm right in the middle of it with a 6-foot observer height, and the same 12-foot object moves away from me, it's going to now disappear at a whole, as a single point, but now it's going to be at 3 miles instead of 6, right? Because the floor and the ceiling are equally compressing the top and bottom 6 feet of this 12-foot object. So again, this is a function of observer height against tangible walls, ceilings, and floors. It's what's obstructing those rays that are trying to reach our eye and create a contextual image. So if I'm at 300 feet now, let's say, and watch a 250-foot cruise ship sail off into the distance, I would not see it disappear bottom first. It would disappear as a whole, like a small dot, at a distance d equal to 250 feet divided by the tangent of the 1 arc minute angle, or 135 miles. And it would disappear at 135 miles if I were 400, 500, 1,000 feet high, and so on. If I were at 30,000 feet, I still cannot make out a 250-foot object 135 miles away, because that is the point theta is met for any object in my visual field regardless of the horizon. Again, you can compress that angle sooner and get that angle to occur sooner against another tangible object, but when looking at essentially no obstructions, theta is the absolute limit. The preferential loss of information bottom first only occurs for objects that are viewed closer to the ground, because we have set our lower horizon line there earlier. So again, this is a function of 1-point perspective and the diffraction limit creating the vanishing point or line by virtue of a differentially compressed visual field. If I were to point my gaze to the sky and my lower 50% of my vision is no longer compressed against the ground, I would view a 150-foot plane traveling straight away from me disappear at a point roughly 81 miles away, again as a single point. If I watch the same plane against the ground, it starts to set into my lower horizon at 3 miles, because my lower horizon has been set by the lower arc angle at 3 miles at a 6-foot observer height. So again, here we can diagram some of this here with our lowered perspective line. You can see how the orthogonal lines are more spread out along the lower visual field, and they are a little bit steeper along the upper visual field. And so for the orange cruise ship here, I've started it out completely below my eye line. So if that cruise ship's 250 foot tall, I am 250 foot tall watching it sail away from me. And it will remain below my eye line the entire way and disappear as a point. But now let's lower our observer height. So now I'm no longer 250 feet high. Now I'm 125 feet high, and I'm watching my eye line, or my eye line is now in the middle of the cruise ship. And I watch this same cruise ship sail away. Well, I've set my lower horizon in sooner than before. And so I am now going to have the bottom of the boat disappear first, and the top will remain visible for a longer time, and the boat will disappear bottom first. I have lowered my eye height, and I have brought my lower horizon in sooner. So again, when does the green ship completely disappear? If let's say I'm 100-foot observer height, which is roughly the midpoint of the ship, we know that 100 feet is lost at 54 miles, assuming no upward refraction, which we'll get into later. So the remaining 150 feet above our eye line continues to descend into the horizon for another 81 miles. You will likely lose the boat from atmospheric haze and those illumination issues that we've discussed, upward refraction issues, which we'll also discuss long before that distance, but that is the concept for diffraction. So essentially what I want you to take away from this is that if I'm looking at a certain size object that is completely unobstructed against another object, and it's like up in the sky, let's say. I will observe that object get further and further away from me and get smaller and smaller and smaller as a whole, and it will disappear as a point, essentially into my vanishing point. However, if I bring that same object, let's say it's at 30,000 feet high, and I just rotate that object and my visual field down to meet the ground, once I get close to the ground, and that object gets close to my horizon line, down near essentially the 3 mile mark, which is as far as I can see when I'm compressed against the ground, that object will start to set into the ground. So as a practical example here for this, mainly what I want to discuss here is the linear relationship between height gain and object observation. So how much you can see of an object with your height. So as a practical example, an individual filmed a cruise ship from a beach at a 6-foot elevation, video link in the description. When the boat has lost roughly 6 decks or so, he then climbs 30 feet to view more of the boat. But since he raised his observer height 30 feet, he decompressed those lower 30 feet worth of angles, and he essentially sees 30 feet more of the boat, or roughly 3 to 4 decks. And so again, he just raised his observer height to 30 feet higher, so he just sees 30 feet more of the boat. And we already described this relationship. This is just h1 over h2 equals to d2 over d1. So here in the photos, I'm just describing those two horizon lines and what he's gained with each one. And over on the these are the zoomed out photos on the left side there, and then zoomed in on the right. The black arrows pointing to what he's looking at. So as another caveat to eye observer height, if you are at the same height as the object being observed, again, it will not decline from your horizon without some kind of upward refraction. The top of the object nearby will remain at the same height as it moves away from you, just underneath your eye line, until it disappears as a whole, bottom up. So recall from part 2 where we had our observer at the base of the mountain. If we place the observer at the top of the mountain and the mountain were to move straight away from us, the top of the mountain, minus refraction effects again, would never recede from our eye line. That tip of the mountain stays right where it is the entire time. It would simply shrink as a whole, and the base would be continually being brought upward to meet our eye line, again because the floor meets the ceiling within perspective. This is because the mountain is below us and is part of the ground underneath. So again, in our orthographic representation on the upper left there, you see that the, let's say, 4 mountains are in a straight line away from us, all of equal heights. And when we model that into perspective, you see that the mountain tips stay right along that purple horizon line as they ascend with distance and rise towards that horizon as they get further away. And eventually they will disappear. If we kept modeling this, the mountain would disappear as a single point based on its height. So here's a practical example. This observer is at roughly the same elevation as the nearby Frying Pan Mountain on the right there. So he is at, you can see his altimeter there, for 5,382 feet. Frying Pan Mountain is 5,380 feet. And then there is the very distant mountains, which are roughly 39 miles away. We'll just take Graybeard Mountain, for example, at roughly 5,395 feet, and you can see that it is essentially in line with the nearby mountain. But the same phenomenon would occur, would be visible for a 5,300 foot mountain 100 miles away. If you were able to see it, it would still be the mountain tip along that straight line, along that purple line, give or take. Again, some refraction issues will come into play, but if you are minus refraction, it will be exactly on that purple line, if it is exactly the same height. Again, the top of it would still be on or near your eye line minus refraction, but the bottom is going to be coming up and up and up to meet that line, and that mountain is going to be disappearing as a single point. So if theta is met below the horizon and not above, the object disappears below our horizon and not above. Recall that the angular compression rate is determined by observer height. So we're just using some diagrams here to represent this. The loss of information occurs only for information within a 0.02 to 0.03 angle. So you can have an object 0.02 degrees above your eye line disappear, 0.02 degrees below your eye line disappear, and so forth. So again, our horizon represents all information contained in less than 0.02 degrees above or below the eye line. And put another way, our horizon is comprised of plus 0.02 to minus 0.02 degrees on either side of the eye line, assuming that we have equal floor, wall, and ceiling compression. But now if we have differential floor, ceiling compression, and let's say theta is only met below our eye line because we're now closer to the floor, and the floor is taking up more and more of that lower 50% of our vision. And so if we reach theta for only the bottom of our eye line, a 6-foot person is completely lost at 3 miles, and an 18-foot tower, let's say, is only partially lost, and again it occurs bottom first because we've met theta only in the bottom visual field. Also, recalling our building example, there's a concept of our personal horizon and what we believe to be a true or physical horizon. For as far as we can tell, though, the sky never actually physically meets the floor. But when we match up our eye line to a point roughly parallel to where the ceiling and the floor appear to meet, we can see these optical phenomena better. So again, I can be looking up at the sky, but once I place a tangible object against my visual field, it will become a compressed visual field angle, just like it is when I am looking against something along the ground. So essentially when I'm looking against the ground, against something, I'm just providing a better backdrop to view this effect. But this effect takes effect sooner and sooner the closer and closer I get to the ground. So if I put my eye on the ground, I've brought my horizon in much, much nearer. But again, keep in mind, angular resolution limit exists everywhere, no matter if we're looking at the horizon or straight down at our feet. Just like if I am looking at a human hair on the ground, there is a point where it will not be seen, and that point is theta. So if I look up the side of a tall building, the building becomes my floor, and the same effect occurs. So if the building were, say, a mile high, 5,280 feet, where you are close by and looking up, you won't see a person waving out of the top windows. So as an example, these buildings become the visual floor here within this example. That building on the bottom is now our new floor. An object within theta near our horizon is lost, according to the same rules. Keep in mind, though, within this picture, these buildings are parallel to one another. They're not curved. Yet if the buildings were taller, you would see a window washer or window painter or someone ascending high up. They would disappear building side first as they ascended if they reached beyond the purple horizon line. And there were no, the other building, let's say, was not within the field and not obstructing your vision. So with that in mind, let's see what happens with a lowered eye line and an object just to our left. Returning to the principles of perspective, you will notice the more dramatic changes in height are seen at the top than at the bottom of the object when we lower our height. As the object gets further away, the changes we observe at the bottom somewhat stabilize relative to the top, and we see things descend top down more dramatically than we see things ascend bottom up. So just pull out some rectangles and place them against orthogonal lines and stratify them, and you'll see the effect. So here in the lower left diagram, I have a equal horizon point. I am equidistant from the floor and ceiling, and I have some kind of colorful building, let's say, moving further and further away from me in a straight line, and the points all equally diminish in size according to these orthogonal lines. You see how the tips of the building, it's stratifying downward and upward along those orthogonal lines. Now let's lower my observer height, and now I've compressed the lower transversal lines, and the upper transversal lines are now wider and more spread apart. So the descent rate is a little bit steeper on the top and a little bit more shallow on the bottom. But what that means for the bottom is that the bottom is going to get merged quicker than the top. The top is going to remain more distinct because it has a sharper, more distinct drop angle. And you can see that effect here. When I lower down my horizon line, this purple line, you can see the yellow, green, orange, and black become a little less distinct a little sooner. And so if we zoom in here, you can kind of see what's happening. So I'm going to zoom in on what's happening at the very far away point there. You can see that within the transversal lines, those horizontal lines that are parallel to the horizon line, those boxes essentially, those boxes along the bottom get closer, the same box, right, which is what's containing that building. The lower part of the box gets closer to the purple line a lot sooner than the upper part does. The upper part is still distinct. So at a certain point, though, before that purple line is breached by the lower edge of the box, the theta, the angular resolution limit, is breached, right? And so that part of the building disappears. But the top part of the building is still at a wide angle. It's still visible. And so it continues to descend from that point at its rate along that orthogonal line. So hopefully that makes sense. So again, this is not Earth curvature. This is just these transversal lines on your lower visual field. They are more compressed than the upper ones. And so you start to lose that contextual information a lot sooner. Those rays merge. You cannot distinguish what an object is. It does not create an image on the back of your retina. This is Airy's criteria. So when you try to model this, you can do this for yourself too. I've used a boat or some other object to have part of it ascend along the bottom of my visual field and part of it descend along the top, maybe a larger amount of it. And what ends up happening is you get down to 1 pixel along the bottom of the boat a lot sooner than you do along the top. But the software usually always wants to keep 1 pixel. It doesn't just, lose the pixel. And so you have to do that part manually, but the concept is the same. You get down to 1 pixel a lot sooner along the bottom when you do this. So again, just to reiterate the point, an object never completely disappears until 2 theta is met or the top sets into the bottom horizon, one or the other. Again, so it would be 2 theta for if I had, let's say, a corridor. I was looking in a corridor and I was equidistant from the top and bottom. The resolution angle would be met as the top part descends away from me and as the ceiling compresses that object, and the other part of the object would be compressed against the floor, and it would disappear when it reaches theta. So an object wouldn't disappear until 2 theta if I'm in an equidistant corridor. But if I go outside and I know I lose the ceiling, let's say, and I'm only compressing the floor, well then the floor is the only thing where I reach the resolution angle against sooner, and then that is going to disappear first. So again, 4 rays are necessary for an object that exists above and below my eyeline, right? I need 2 rays coming off the top of the tree, and I need 2 rays coming off the bottom. They are going to intersect and create an inverted image like we talked about in part 1. So we may perceive that we see the tops of something far longer than the bottom, again, because the angles above our eyeline are much less compressed than below. We still have the same number of angles above and below, but with the lower observer height, the bottom angles are far more compressed and the paired angles above expand. So you can model this with, again, just lines and a single point and 2 parallel, a ceiling and a floor, let's say, and you can move the observer height within those multiple lines up and down, and you will see that as the lower lines compress, the paired angles above expand. And so the total number of potential angles above and below the eye line are the same, since we have similar numbers of rods and cones circumferentially positioned around the fovea. But when we alter our observer position, the information alters. So if we lower ourselves to the floor, the angles above the eye line get wider, I see more of the ceiling, and the angles below become smaller, I see less of the floor. But again, the floor is taking up 50% of my vision, the ceiling is taking 50% of my vision. I'm seeing less of the floor within that 50%, and I'm seeing more of the ceiling within that 50%. So I've kind of modeled that here. Again, I'm kind of equidistant with the top example of the bottom diagram. And my observer height isn't artificially lower or higher, it's just right in the middle. And when I collapse those lines, they will you will have a bit of a longer horizon distance. And when you collapse your observer height down, those lower angles compress, the upper angles expand a little bit. But because I've artificially compressed the lower angles to a higher degree, theta is reached sooner for the lower horizon is essentially brought inward, and the upper horizon isn't met, and it collapses downward over the top. So let's develop this paired angle idea a little bit further, and then we'll get close to the end here. So if we assume we have two equal balls, let's say these gray balls at a given size nearby at angle 1, one is above us and one is below. As the objects move away from us in a straight line, let's say along the ceiling and along the floor, they are observed with progressively smaller angles. So again, just model out those angles, which I've modeled here in blue, and I've modeled the resolution limit in orange, let's say. Once theta is met, both of those objects disappear. So again, if you look along angle 1 through 12 up at the top, the object just gets smaller and smaller away, or smaller and smaller as it moves away. Once it hits that angle 11, in this example, then it is no longer observed. It's too small to be seen, and anything if it were to move beyond into angle 12, it's not observed. And so again, I have placed these objects in an orthographic representation, and I'm also diminishing them in size. So keep that in mind. When you do model things orthographically, these would stay the same size, but I'm just trying to show you how it would look prior to me collapsing down the ceiling and the floor. But once I collapse the ceiling and the floor down within perspective, they are going to represent those sizes. So again, this is just illustrative for kind of what's going on. Now assume the same scenario where we have two equal balls at a given size nearby at our angle 1. The ceiling is very high now relative to the floor. The ceiling is higher up. I'm now very low down, closer to the floor. The balls are still observed at angle 1 again. But the small ball is now further away, so it's smaller, right? So the one above us on the ceiling is further away because the ceiling is higher, so it's smaller. The one below us is a little closer to us, so it's bigger. But theta is now met at angle 8 along the bottom because we got closer to the ground. So angle 8 is now our new resolution limit. But along the top, that corresponding angle 8 is nowhere near compressed. It's still very wide open. And it's almost similar to angle 4 and angle 2 and angle 6 and so forth. So the top theta is now paired with an angle well beyond angle 8 below it. In other words, if I were to extend this diagram far off the page, or far off the screen, then when I do meet that 0.02 angle, which is these two orange lines above the purple line, when I reach that angle above my eye line, that's paired with like angle 400 along the bottom, let's say. So it becomes much more dramatic when I lower my lower visual field and reach that angle sooner. You just won't see things compress within the upper visual field anymore. They will now, as they descend, as you collapse the ceiling and the floor at this point, they will now set into your lower visual field. You will not see them disappear as a point because that resolution angle is now far off to the right, essentially. So here we're going to collapse them, and you can kind of see what's going on. So when observing this scenario, theta is met for my lowered observer height, and it sets my lower horizon distance, which is now closer in at angle 8. For the information above my eye line, the descent rate is now steeper, but I have less of an angular compression rate. So these angle pairs, the 8s or the 1s or the 11s, let's say, must always remain in proportion, but they diminish together according to the ceiling and floor distance. If one angle decreases, the other increases, but they are both diminishing with distance. Theta is never met along the top because the horizon distance is nearby and is set by my lower compressed visual angles. It's set at the bottom. It occupies 50% of my vision. So wherever the information above my eye line is at that point, when these two halves collapse, is what I see above my eye line. And it continues there until it sets completely within the lower horizon. So again, the top continues on independently, but you'll never see the object diminish in size and reach theta itself because it's already set into your lower horizon by that point. Note also the steeper descent rate along the top. The higher the ceiling, the steeper the descent rate within our perspective. That's how our brain interprets it. The nearest ceiling or floor sets our horizon. Similarly, the nearest wall would set the vertical vanishing line if we wanted to model it that way from top down. So again, here's our orthographic representation on the left. And then when I collapse it, you see now how the balls, they would diminish in size. So because the angles from 1 through 12 along the top aren't much different from one another now, the ball essentially remains the same angular size and just diminishes. But along the bottom, it's much bigger, right? Because I'm closer to it, so it's much bigger to start out with. But it gets smaller a lot sooner and reaches theta a lot quicker. So again, another thing to note here too, you see potentially all the way to 12 along the upper visual field for that object moving away from you. But along the bottom, again, you still only see to about 8 because you've brought your lower horizon in sooner. And we'll go over this a little bit later, but as far as how far I collapse these two to reach the vanishing point, like what angle do I use to collapse them, essentially you collapse them to your vertical field of view, which is about 65 to 68 degrees. So you rotate essentially the ray extending to angle 1. That ray is about 65 degrees to your eye line. And then the ceiling, right, which is the blue line that has all the numbers across it, that then just rotates, swings downward until it hits the lower vanishing point, and that's how you create that. And that's what I think is happening within these representations, as we'll see in a minute. So when I model this thing into perspective, into 1-point perspective with a lowered horizon line or lower observer point, you see now that I see a larger ball extending off and becoming smaller much more rapidly than along the bottom than I do along the top, and the top remains somewhat stable as it descends and sets into my lower horizon. So you may have already guessed this, so the sun is a practical example. So the sun and moon set because they travel a short distance in a straight line along the very high upper boundary. So if we extend our ceiling to a tremendous height, let's say, you see that the rate of differential angular compression between the floor and the apparent ceiling is very large, and the descent rate steepens dramatically. And so I'm just modeling that in the lower left. So you see how the angles get much wider when I extend the floor to a very large height. This is just 3, 4, 5 times higher, in this case about 3 times higher, but you can see the effect on those angles. So the object descends to the vanishing line rather quickly while maintaining a relatively constant resolution angle as it travels. So again, if you just go back to that previous page with the 1-point perspective and that ball that didn't really change in size much as it descended and set into our lower horizon, as we extend the ceiling up higher, this effect is even more amplified. and it retains its angular size for a very long time, and it only changes minutely in size. But again, once it hits my lower horizon, it's going to set just like an airplane would, just like a cruise ship would, descending bottom or disappearing bottom first, just like a flashlight would along the ground when we do the long floor examples. It's the same exact phenomenon. It's the diffraction limit. It's the angular resolution limit of the observer. So we can show that here. So to visualize that, let's return to our perspective diagram that we subtracted the walls away from in part 2. And we're now going to just, let's say we get a little bit closer to the ground relative to a very tall ceiling. We're going to raise the ceiling incredibly high away from us, and then it's going to collapse down within perspective. So we're going to see, relative to this very tall ceiling, we're going to have we'll say we have much more compression of a floor relative to it, and much more wider angles at the ceiling. So the ceiling is going to expand to that rate, the floor is going to compress to that rate, and an object traveling along a very tall ceiling away from us, if it's of sufficient size enough to be visualized at that tall height, would have a relatively very little change in angular size, as it would set into that highly compressed lower horizon. So let's return full circle to our light on the floor example that we showed earlier, and we'll see that we created essentially a mini sun. And we are assuming that the floor is flat and level. The person far away is simply placing the light toward the camera and raising and lowering it from the floor to their waist. The observer height, which is the iPhone camera with a small aperture and larger theta, is on the floor, lens side down, so again closer to the floor. The video is a bit fuzzy because it's zoomed in here for you to see it, but I took a screenshot of the native video and placed it there on the lower left to kind of see again that the floor is still the 50% mark of that perspective view of that observer, but it's a lot more of the floor is compressed within that 50%. And so again, theta has been reached at this far distance. So the floor set my lower horizon, and some distant parts of the floor have vanished in this shot. So that's now my horizon limit. And the LED light, which is what I've shown here with the picture here in my hand, will set into it. So we will see later that magnification doesn't alter perspective, so it doesn't alter the transversal lines that were compressed against the horizon line with it to create theta. You can just zoom in on that thing, but if it's been lost, it's been lost. So again, we'll discuss magnification here in a minute because there's some caveats to all that. But let's show this example here. So apologies for the movement. It was my fingers trying to stabilize the tilt of the camera, but you can see the effect. So and I put it on a loop. I apologize. It's just an 8-second loop here. So you can see that she is lowering the light down. It's disappeared. It's brought back up. And as she keeps doing that, you can see it set into the lower horizon, as if it were like a mini sun. So this said, the sun doesn't set entirely due to perspective, I don't believe, but I think it's a significant part of it. There is likely some kind of personal atmospheric lensing effect that explains star trails and other phenomenon, such as reflections under clouds and many effects of the sun and so forth, such as the sun may be like a rear projection or something to that effect, and we don't actually know where the actual object is above a like personal atmospheric lensing system, let's say. But there's a great video on that, and I'll leave a video link in the description for that video. So let's now return to our bottle example before we close up here. We asserted that if the angular resolution limit of the observer is unknown, you can calculate it for the amount of the object that is cut off at a known distance. Once calculated, you can use that angle to calculate a height change with a known distance change or a distance change with a known height change. So we'll use MRAD designations, which are just 1/1000th of a rad, where 2 pi rad equals 360 degrees, or rad is equal to 180 divided by pi, which is 57.3, which is what we talked about a little bit earlier. So this method is especially useful for angular size comparisons with a known distance or height within the same theta. You can use the ratio of the height and distance of the unknown object if the angle is the same between the two. Again, just like we talked about earlier with h1 over h2 equals d2 over d1. So within this bottle example, you can see here we know the following from this, and again a video link is in the description. We know that the bottle is 3.5 inches tall, the observer is 107 feet away, and it appears that the bottle has a height of 12.5 millirads, or 3.5 inches per 12.5 millirad, or 0.28 inches per millirad. And so if you need to pause and kind of look through that math, that's fine. But essentially, the part of the bottle that's been cut off, I modeled as 1 millirad. So approximately 1 millirad is cut off from the bottom, or 0.28 inches. So our height that is cut off now is 0.28 inches, and our distance we know is 107 feet away. And 0.28 inches is roughly 0.0233 feet, because you got to put this in the same units, don't forget that. So you can model that within our low angle far distant right triangle, and tan theta is equal to height divided by distance, and so you get the height that's lost of 0.0233 at 107 feet, gives you that angle of 0.012 degrees, which is a little bit less than 1 arc minute. So this angular resolution is pretty good, but it represents this camera at the predominant wavelength and aperture diameter with which this object was observed. So with theta known, you could predict how far you are with how much of the bottle is cut off, or alternatively, how much of the bottom is cut off by how far away you are, just by using that triangle and a known angle. And you could also use this angle to then say, if I got up a little bit higher, how much more further could I see, right? Because h1 over h2 equals d2 over d1, holding the angle constant between the two. We'll do another example after discussing some refraction effects later on in the series, but we need to discuss some things with Polaris and magnification here and the angular size of the moon real quick. So before moving on, as an aside, you can also use angular resolution to see how far away something is. Take the sun and moon, for example. The moon fits within 29 to 34 arc minutes of vision. This is the theta at which the moon is observed to fill. That's its angular size. If we don't know the true object diameter or distance, we can gather a range of sizes and distances that scale to one another according to that angle. So again, in this case, we're going to use 30 arc minutes, which is 0.5 degrees. You can roughly use your hand to get a angular resolution or angular size of an object. A fist is 10 degrees. Extending your pinky and your thumb gives you 2 fist widths, or 20 degrees. 3 fingers is 5 degrees, and your pinky is 1 degree. So in this case, we'll use 30 arc minutes, 0.5 degrees. Our sun, or excuse me, in this case our moon, has a unknown diameter and an unknown distance, but we get a ratio of 0.0087, which is what the diameter and distance would have to fit within for it to retain that angular size. So diameter and distance must relate by a factor of 0.0087. So if the moon is 238,000 miles away, its size is 2,070 miles in diameter, and vice versa. If you knew that its diameter was 2,000 miles, you would calculate its distance based on that ratio. However, if the moon were 3,000 miles away, its size would just be smaller. It would be 26 miles in diameter, because that also works. Likewise, if it were 300 miles away, it would be 2.6 miles in diameter, and so on. Interestingly, the sun also takes up the same 30 arc minutes of our vision. So we have our 2 lights in the sky taking up essentially the exact same angular size as one another. So they could be exactly the same size for all we know. We will see how the angular size of the sun and moon are observed with perspective later on, but you need to have two objects, one near with a known distance and height, and one far with a known distance or height, to get an accurate angular size or distance of the far object. We don't have that for the sun and moon, so if physical objects, if that's what they are quite possibly the same size. As a caveat to this, Aristarchus in 300 BC assumed the lunar eclipse was the Earth's shadow, but without this assumption, all of these sizes and distances fall apart. Also, because Polaris is roughly 90 degrees above us, we can use it to estimate latitude if we assume it has a fixed position. If we use an astrolabe or a sextant and measure the angle between horizon and Polaris, we will get a latitude. On a ball, it should be physically impossible to view Polaris beyond the northern hemisphere because you will have gone over the curve, and you do not have a tangent line to that point anymore. They make Polaris such a vast distance away so that you can assume at least it's a parallel line coming in across all points along a hemisphere, and parallel with the, or tangent with the equator. No tangent, again, exists in a straight line beyond 0 degrees at the equator, though, because, again, they are blocked by curvature. Polaris, however, can be seen as far away as 23.4 degrees south of the equator, which is the Tropic of Capricorn. So to make the math work, they tilted the Earth, and the new equator became 66.6 degrees to Polaris. Now suddenly it was okay again for people to see it from 23.4 degrees south, as well as other celestial observations. So here we have our Earth and our distant star coming in. We could model this as very distant, very far away, and it could assume parallel lines. And then we cannot see it at this point at 23.4 degrees south, but if we then tilt the Earth 66.6 degrees to Polaris, then we can see it again. It creates a tangent line that is acceptable. But an alternative explanation is that Polaris sets at 23.4 degrees south into the lower half of our visual field when it is an apparent distance of 7,800 miles south. But again, actual distances may not represent reality because of a possible projection phenomenon. So the way you get that 7,000 miles is assuming accurate latitude. Each degree of latitude is 69 miles, so that makes Polaris at least 23.4 degrees south plus 90 times 69 miles, so 7,824.6 miles away. Since it only makes a brief appearance above the eye line or horizon at 23.4 degrees south latitude. It also means we can see celestial bodies potentially at least projected 7,000 apparent miles away for a circle diameter of vision of roughly 15,000 miles. And we've modeled that here with some of these angular sizes to Polaris. And we will go through this in part 5 in much more detail. And lastly, on magnification. Magnification can be thought as the ability to see an object that is subject to preset compression angles. You are not getting closer to the object, you are bringing an already compressed distant image closer to you and peering inside those compressed angles. There are some changes in aperture, focal length, etc. that do affect resolution angles, but think of it conceptually as peering deeper into the set perspective and compression that is already present at your distance. You do not change your transversal lines, and where those transversal lines have met theta, you just peer deeper in within those preset lines. But however, you cannot resolve something less than theta, no matter your magnification, or I should say no matter your zoom. The angles are set. You just effectively bring your eye closer in. Perspective is observer dependent. So if you were to change your camera position by getting closer to the object or higher up, you would see more of the object due to larger angular resolution and alter perspective and decompressing those angles. But without changing your position, in all cases, no matter what variables we manipulate, and I'll say magnification, but specifically I mean zoom, does not alter the perspective of the observer. It only magnifies what you're seeing. So again, here within this perspective shot, without magnification on the left, you're seeing this entire field, but when you zoom in on the central rectangles, transversal lines, you're just making them a little bit larger, but the perspective is still there. So if an object has disappeared beyond the purple horizon line, you can't bring it back by zooming in on it per se. Again, there are some tremendous amounts of zoom that do seem to bring back things that are incredibly pinpoint small. But by and large, zoom by itself doesn't bring things back. But I want to talk about a little caveat here. So as a caveat, this is more related to the zooming in and out of objects within a set perspective rather than the magnification by the comparison of two separate observer camera systems. So if an object is cut off at the horizon for a given observer, diffraction cannot be overcome by zoom. Zooming in only enlarges what you're already seeing, what's already being captured by that observer at that aperture and at that wavelength. So when you're zooming in, you're essentially diminishing the aperture. You're not making it wider. You're not resolving more. You're just bringing what is there, enlarging it, and seeing it a little bit better. So hopefully that distinction makes sense. If I change observer systems to something that has a wider light gathering ability and a wider aperture at a given focal length, now I have now I can get greater resolution and potentially bring something back from beyond a lost horizon. So every system has a limit though. So if an object is cut off at maximum zoom for a particular thing, further movement away cuts off more and more of that image. So again, horizons are set by diffraction limitations on a particular observer system with a set aperture size and wavelength that it's gathering. So again, cracking these codes is collaborative as always. Thanks to everyone who's been doing great work. So these were the objectives. And so hopefully we discussed angular resolution, Airy patterns, Airy disks, Rayleighs criteria, diffraction limit, the differential angular compression and resolution of images above and below the vanishing line, angular size, stability of the sun and moon, the cause of a sunset, the importance of Polaris with regard to distant vision and position, and we will cover that in more detail in part 5, and the effects of magnification on perspective. So in the next part, we're going to discuss the inferior mirage and the horizon, refraction effects across bodies of water, and a summary of angular compression before moving on to the derivation of a Earth's radius.